Now, the change in energy of a system, that is a state function. That means that the change in energy is just the energy of the system after a process minus the energy of the system before a process, regardless of how the reaction or process occurred. It's like height, a change in height. Whether you go straight up a mountain or if you go round about the mountain, if you start at the same place and end at the same place, both pathways have the same change in height. And so this state function character of energy also applies to delta H, enthalpy, change in volume, change in pressure, and change in temperature of a system. And so we can use this concept in explaining Hess's law. Now, Hess's law says that an overall process, the change in enthalpy of that process is the same whether it's just immediately done in one step or done via several steps. And so what that means is we can add and subtract steps in a reaction to find the change in enthalpy of those individual steps. So for example, here we're looking for what is the change in enthalpy of turning carbon in its graphite form into carbon dioxide by reacting with one oxygen. Now we can find this by finding information about smaller parts of that reaction. So we know that the energy of a partial combustion of carbon, turning carbon into CO gas, is negative 110.5 kilojoules per mole, and that the energy of, or enthalpy of further combustion of that carbon monoxide into carbon dioxide, that has an enthalpy change of negative 283.0 kilojoules per mole. And so if we know the delta HB here and we know the delta HC here, we could theoretically add them up to find the delta H of the overall process. Now, this delta H is equal to delta HB plus delta HC. This only applies if the reaction, the overall reaction A, is the same as the overall reaction B plus the overall reaction C. So we want to test that here. Is this overall reaction A the same as reaction B plus reaction C? So what we want to do is add reaction B and C up to see if we get reaction A. So what we can do is just, I guess, anything on the left of the arrows here, just put it on the left in the combined B plus C reaction. So carbon in its graphite form plus carbon monoxide gas plus, let's see, 1 plus half plus 1.5 O2 gases. Okay, and then on the right we have a carbon monoxide gas and a carbon dioxide gas and half, or 0.5, of an O2 gas. So, is this reaction B plus C the same as reaction A? Well, we need to cross things out before we check. So, what is on both sides of the reaction? Carbon monoxide gas is on both sides. Also, you can remove half of an O2 from both sides so that you have one O2 left here instead of 1.5. So, we have one carbon graphite form plus one O2 gives one CO2. And we have the same thing in reaction A. So, reaction B plus C is the same as reaction A. B plus C is the same as the reaction A, which means, therefore, that the heat of reaction A is the combination of the heats of reaction B plus C. So, knowing the heats of these two reactions, we can combine them, and we can find that the heat of the overall reaction A is, let's see, negative 110.5 plus negative 283.0. It's negative 393 3.5 kilojoules per mole of carbon in its graphite form, which is combusted fully into carbon dioxide. And if you like, you can copy down Hess's laws here. It says Hess's law is that the change in enthalpy of the reaction is the same whether it occurs in one step or several, and that you can add up reactions and their heats to find the heats of other reactions. There's going to be a part B. Watch it. Thanks, guys.